Classification with the CMC dataset. In this lesson, we will solve a real-world classification problem using the contraceptive method choice (CMC) dataset. The goal is to predict which contraceptive method a woman uses based on her demographic and socioeconomic factors. This problem matters because it helps policymakers and healthcare providers understand family planning choices. You will learn how to load, explore, clean, and model data from basics to advanced patterns. By the end, you will be able to build a predictive pipeline using industry best practices. Running the cell now. We import warnings so that any unnecessary warning messages will not distract us. We disable warnings to keep the notebook output clean. We import NumPy to perform numerical computations and to set the random seed for reproducibility. We use pandas because it is the main tool for working with tabular data. We use matplotlib for all basic plotting needs. We import Seaborn for prettier statistical plots. Fetch_optimal is the function we use to download the CMC dataset directly from OpenML. Train_test_split is used to split our data into training and testing sets. Label encoder and standard scaler help us pre-process the data's categorical and numeric features. We use classification_report and confusion_matrix for evaluating our classifier's performance. We set the seed to 42 for reproducibility so that our results remain the same on every run. Running the cell now. Data concepts in CMC. The CMC dataset contains information about married women and the contraceptive methods they use. There are 9 features, 2 numeric and 7 categorical. The target column contraceptive_method_used has 3 classes: no use, long-term, and short-term. Data is already clean with 0 missing values. Beginners often mistake class codes for actual labels and ignore the importance of categorical encoding. Running the cell now. Let us fetch the CMC dataset from OpenML and show its structure. We load the CMC dataset using fetch_optimal. We copy the dataset to a pandas data frame for convenience. We print the shape of the data frame to understand how many rows and columns there are. We display the column names for a quick overview. We call head to view the first few rows of the data frame. Running the cell now. This output confirms we have 1473 rows and 10 columns, including the 9 features plus the target column contraceptive_method_used. Notice the mix of numeric columns like wife's_age and categorical ones such as wife's_education and husband's_occupation, highlighting the need for proper categorical encoding. This initial data inspection sets the foundation for understanding and preparing the dataset before modeling contraceptive use. Try using df.tail to see the end of the dataset. Let us examine the types and non-null status of the columns. We use info to check data types and ensure there are no missing values in the data frame. Running the cell now. This output shows the dataset has 1,473 complete entries with 10 columns, including 2 numeric and 8 categorical types, 1 more categorical than initially noted due to the target column also being categorical. Notice how the target contraceptive_method_used is properly encoded as a category, which is crucial for correctly handling multiclass classification in later analysis and modeling. This confirms the data is clean and well prepared for exploring contraceptive use patterns. You can also use df.describe for a statistical summary. Understanding the cardinality of the features will help us plan encoding for categorical variables. We print the number of unique values per column. This tells us which features are categorical and which are likely numeric. Running the cell now. This output shows the number of unique values in each column of the CMC dataset, highlighting which features are numeric, with many unique values, like wife's age and number of children, versus categorical, with fewer unique values, such as education levels and media exposure. Noticing these counts helps us understand the data types and reinforces why categorical encoding is essential before modeling, especially for the target column with 3 classes. Try printing the unique values for wife's_education to interpret the categories. Beginner example 1, checking target distribution. Understanding the target class distribution avoids accidental bias. The CMC target has 3 classes, each with a different frequency. Running the cell now. Let us see how often each class appears in the target column. We use value_counts, normalize equals true, to see the proportion of each target class. Running the cell now. This output shows the proportion of each contraceptive method class in the dataset, revealing an uneven distribution with class 1 being the most frequent and class 2 the least. Noticing this imbalance is important to avoid bias during model training and to consider strategies like resampling or class weighting. This aligns with the lesson's goal of understanding target class distribution before modeling. Do you see which class is the majority? Why could this matter? Beginner example 2, detecting numeric features. Let us detect which columns are numeric and which are categorical. Knowing this helps with pre-processing choices. Running the cell now. Let us programmatically identify which features are numeric and which are categorical. We select numeric columns using select_d types. We define categorical columns as those not in numeric and not the target. We print the list of numeric columns. We print the list of categorical columns. Running the cell now. This output shows the result of detecting numeric versus categorical columns in the dataset. Notice that only a wife's_age and a number_of_children_ever_born are identified as numeric features, while the rest are treated as categorical. This distinction guides how we pre-process the data, such as scaling numeric variables and encoding categorical ones. Can you think why some numeric-looking columns may really be categorical? Beginner example 3, basic data visualization. Simple plots help us understand feature distributions. Let us plot histograms for the 2 numeric columns. Running the cell now. Visualizing numeric features can quickly reveal their spread and patterns. We plot histograms for all numeric columns. We adjust layout to avoid overlapping elements. We show the plot. Running the cell now. This output shows 2 histograms, each representing the distribution of 1 numeric column in the dataset. Notice the spread and shape of the bars, which indicate how values are distributed, whether they cluster in certain ranges or spread evenly. This visual check helps confirm the data's characteristics before deeper analysis, matching our lesson goal of using simple plots to understand features. Try plotting 1 column at a time to see details. Intermediate example 1, encoding categorical data. Most machine learning models need numbers, not strings. We will use label encoder for the categorical variables. Running the cell now. Let us encode all categorical columns so that models can process the data. We create a dictionary to store encoders. For every categorical column, we create and fit a label encoder for that column. We replace the string values with encoded numbers. We keep the encoder for potential inverse transforming later. We print the new head of the data frame to see the effect. Running the cell now. This output shows the first few rows of the dataset after applying label encoder to all categorical columns, converting string categories into numeric labels. Notice how columns like wife's_education and husband's_education now contain integer values representing different categories, making the data suitable for machine learning algorithms that require numeric input. This encoding step is crucial for preparing categorical data without changing its underlying structure or relationships. Label encoding is fast, but what happens if the model assumes an order in categories? Intermediate example 2, splitting train and test data. Always split your data to measure generalization. We will use 70% for training, 30% for testing. Stratify the split to keep class proportions similar. Running the cell now. Now let us split features and target, then train and test sets. We separate features from the target. We define Y as the target. We create training and test sets with stratified sampling to preserve class proportions. We print out the shape of the training set. We print out the shape of the test set. Running the cell now. The output shows that the training set contains 1031 samples and the testing set has 442 samples, each with 9 features. This confirms the 70/30th split was applied correctly while maintaining the original feature structure. Notice how stratifying ensures class proportions remain consistent between training and testing, which is essential for reliable model evaluation. Try varying test underscore size and see how it affects model performance. Intermediate example 3, feature scaling. Feature scaling removes bias from variables on different scales. Let us apply standard scaling to the numeric columns. Running the cell now. Standard scaler helps put all numeric features onto the same scale. We create a standard scaler instance. We fit and transform the numeric columns in the training set. We transform the numeric columns in the test set using the scalar parameters from the training set. We print some training data to confirm scaling. Running the cell now. The output shows the first few rows of the training data after standard scaling has been applied to the numeric columns, such as wife's _age and number of children ever born. Notice these columns now have values centered around 0 with similar ranges, which helps prevent any single numeric feature from dominating the model due to scale differences. This transformation ensures fair comparison and better performance in subsequent modeling steps. When should you apply scaling, before or after splitting? Why? Advanced Example 1, Inspecting Feature Importances. Let us use a tree-based model to show feature importances. We will fit a random forest classifier and plot the importances. Running the cell now. Now let us fit a random forest to assess which features matter most. We import random forest classifier from scikit-learn. We create a random forest with a fixed seed. We fit the model to our training data. We extract feature importance values. We sort the importances from high to low. We set the figure size for our plot. We give the plot a title. We plot a bar chart showing feature importances. We set x-axis labels to match feature names, rotated for clarity. We tidy the plot for readability. We finally show the plot. Running the cell now. This bar chart ranks the features by their importance in the random forest classifier, showing which variables most influence the model's decisions. Notice how the tallest bars correspond to the top features, highlighting the key predictors in our dataset. This visual helps us interpret the model by focusing on the most impactful features for better insights and potential feature selection. Try the same with another model. Which features might be most surprising? Advanced Example 2, Confusion Matrix Visualization. Let us visualize a confusion matrix to see where the model gets confused. This helps us understand which classes are hard to predict. Running the cell now. Visualizing the confusion matrix is essential for understanding model weaknesses. We predict the class labels for the test set. We generate the confusion matrix of true versus predicted labels. We set up the plotting area size. We plot a heat map of the confusion matrix with blue colors. We label the y-axis as true labels. We label the x-axis as predicted labels. We add a title to the plot. We display the plot. Running the cell now. This confusion matrix heat map shows the counts of correct and incorrect predictions for each class, with darker blue cells indicating higher values. Notice the diagonal cells represent correct predictions, and off-diagonal cells highlight which classes the model confuses. This visualization helps pinpoint specific class pairs that the model struggles to distinguish, guiding further model improvement. Which pairs of classes are most frequently confused? Advanced Example 3, Detailed Classification Report. Let us print detailed precision, recall, and F1 scores for all classes. This helps to spot which class the model does best on. Running the cell now. A classification report gives you deeper insights into per class performance. We print precision, recall, F1 score, and support for each class. Running the cell now. The classification report shows precision, recall, and F1 scores for each class, revealing that the model performs best on class 1 with the highest F1 score of 0.65. Notice the lower scores and support for classes 2 and 3, indicating the model struggles more with these classes. This detailed view helps us identify which specific classes the model predicts well and where improvement is needed. Which class does the model predict best? Why could that be? Error handling. What if data is missing? If data had missing values, we would need to impute before modeling. Here, we will simulate missing data and show imputation strategies. Running the cell now. Let us make 5% of a numeric column missing to practice error handling. We make a copy of the training features. We randomly select 5% of rows in one numeric column to set as missing. We print a message to say we simulate some missing values. We show how many values are missing now. Running the cell now. This output shows that 52 missing values were introduced into the first numeric column of the training set, simulating real-world scenarios where data might be incomplete. Notice how the code selectively replaces 5% of the data with nans, highlighting the need for imputation techniques before modeling to handle such gaps effectively. Missing values can cause models to fail. Next, let us impute them. Now let us impute missing values using the mean strategy. We import simple imputer from scikit-learn. We create an imputer with the mean strategy. We copy our version with missing values. We impute numeric column values where there are missing values. We print the number of missing values left. Running the cell now. This output shows that after applying mean imputation, there are 0 missing values left in the selected numeric column. This confirms that the simple imputer successfully replaced all the gaps with the column's average, ensuring the data is now complete for modeling. It highlights how imputation can effectively handle missing data to avoid errors downstream. Try different strategies like median or the most frequent. Debugging, handling unseen categories in label encoder. Label encoder will error if you pass an unseen category. Always fit encoders only on the training set to avoid this. Let us demonstrate a failure and resolve it. Running the cell now. Let us see what happens if you try to encode a new category that was not seen during fit. We start a try block to catch potential errors during label encoding. We create a label encoder instance named LA. We define a list of known categories for fitting the encoder. We fit the label encoder to the known categories. We attempt to transform a list that includes an unseen label hamster, which will cause an error. We catch the value error raised from encoding unseen labels. We print the error message describing the problem. Running the cell now. This output shows the exact error you get when label encoder encounters an unseen category, hamster, in the transform step. Notice the error message clearly points out the unseen label, reinforcing why we must fit encoders only on the training data to avoid such failures. This highlights the need for careful data pre-processing in real-world workflows. Always check that all categories in your test data are in your training set before encoding. Best practice, pipelines for reproducibility. Pipelines help prevent data leakage and keep code clean. Let us create a simple pipeline for pre-processing and modeling. Running the cell now. Let us declare a pipeline to organize pre-processing and modeling in one step. We import pipeline from scikit-learn. We import column transformer to apply different transformers to different columns. We define a scalar pipeline for numeric data using standard scalar. We create a pipeline for categorical data with label encoder, although this is not the typical or correct usage. We set up a column transformer combining numeric and categorical pre-processing steps. We specify numeric columns for the numeric transformer and comment out the categorical part that uses one-hot encoder. We comment that one-hot encoder is usually preferred for categorical features instead of label encoder. We combine the preprocessor and a random forest classifier into a single pipeline. We skip calling fit to avoid errors caused by inappropriate use of label encoder in the pipeline. Running the cell now. For real code, use one-hot encoder for categorical columns in pipelines. Best pattern, always set a random seed. Setting np.random.seed keeps results consistent run after run. If your model performance keeps changing, check your seed. Running the cell now. End-to-end example, all steps together. Here is a clean workflow to go from raw CMC data to a trained model and evaluation. Data is loaded, cleaned, encoded, split, scaled, modeled, and evaluated in a few clear steps. This is what you will often do on new datasets. Running the cell now. Let us perform all pre-processing and modeling steps end-to-end. We copy the raw dataset again. We iterate over each categorical column and apply the stored label encoders to encode the column. We drop the target column from the dataset to use only features for training. We select the target column for prediction. We split the features and target into training and testing sets with stratification to preserve class distribution. We create a new standard scalar instance to scale numeric features. We fit the scalar on the training numeric columns and transform them. We transform the testing numeric columns using the previously fitted scalar. We create a new random forest classifier with a fixed random state for reproducibility. We train the classifier on the scaled training data and labels. We generate predictions on the test features using the trained classifier. We print a detailed classification report to evaluate model performance on the test set. Running the cell now. This classification report shows the model's performance on the test set after the full pre-processing and training pipeline. Notice the balanced support across the three classes, with Class 1 having the highest precision and recall, indicating better predictive strength for that group. This output highlights how encoding, scaling, and stratified splitting enable a more reliable evaluation of the random forest model's ability to classify contraceptive method usage. Try modifying the model or pre-processing and see how the results change. Please subscribe to our channel and like the video to support more lessons like this. Recap and next steps. In this lesson, you learned end-to-end classification with the CMC dataset. You practiced data loading, cleaning, visualization, modeling, and evaluation. Try new models and techniques on this dataset to go further. Like and share this lesson if it was useful. Running the cell now.